Hello everyone, welcome to MK Academic Solutions. Myself D. Chinna. I am the faculty member of MK Academic Solutions. So in this video we are going to discuss about the chemical kinetics chapter. This is the part 5 of this chemical kinetics. So in this video we are going to discuss about factors effect on the rate of reaction. Okay. So we will discuss about the factors effect on rate of reactions. Some of the important factors I listed here. Okay. So first let us see the what are the factors effect on the rate of reaction. Okay. We know what is the meaning of a rate of reaction. Okay. Rate means speed. Rate is equal to what? Rate is nothing but what? Speed. Rate or speed. Speed of reaction. Okay. So which factors affect on the rate of reaction? So there are several factors are there. So out of them we are going to discuss about the nature of reactants and products, surface area and concentration of reactants, catalyst and temperature, pressure. Okay, so these are the factors we are going to cover here. Okay, first let us see the nature of reactants and products. Okay, in nature of reactants and products, first we are going to consider the physical states of reactants and products. Okay, physical state of reactants and products. Physical state. Okay, physical state. Okay, so physical state means we can consider solid, liquid, gases. These are known as what? Physical states of the reactants. Okay. So now here when you take a reaction, if the reactant is present in the gaseous state, we can find the more rate of reaction when you compare to the liquid state, when you compare to the solid state. Okay. This is the decreasing order of rate of reaction. Okay. So why gas reactions are very fast when compared to the liquids and when compared to the solids. In case of gas molecules, the gas molecules having higher kinetic energy. So due to higher kinetic energy, they collide with each other and there is a probability of giving more effective collisions in case of gases. Okay, that is the reason. And when you come to the homogeneous mixtures, homogeneous reactions are fast when compared to the heterogeneous. Why homogeneous reactions are very fast when compared to the heterogeneous? So we know already homogeneous mixtures means the mixtures which are uniform throughout it. Okay, the mixtures which are uniform. Okay, so which are uniform. Okay, so this mixture is what, children? Uniform. Okay, means here the reactants molecules are mixed very thoroughly. Okay, the reactant molecules are mixed very thoroughly. So that's why here we can observe the more probable collisions, more number of collisions we can observe in the case of homogeneous mixtures. And when you come to the heterogeneous mixture, the mixture which is ununiform. Okay, throughout it, if the mixture is ununiform, okay, or else you take, okay, no? So this if the mixture is ununiform, okay, likewise is there. So such type of mixtures are called heterogeneous mixtures. In case of heterogeneous mixtures, number of collisions are very less. Why? Because the reactant molecules are not mixed thoroughly in case of heterogeneous mixtures. That's why number of collisions are very less. That's why heterogeneous reactions are very slow when compared to the homogeneous reactions. And next, if you see stability of reactant, okay, stability is of reactant. Stability of reactant is inversely proportional to rate of reaction. Stability of reactant is inversely proportional to rate of reaction. Means if reactant is more stable, that will not convert into product. If you want to convert into that product, we need to wait for more time and we need to supply some other factors also. That's why if the reactant is stable, rate of reaction is less. And if product is stable, if product product is stable, if product is stable, okay, if product is stable, so the rate of reaction is more, means stability of product is directly proportional to rate of reaction, and whereas stability of reactant is inversely proportional to rate of reaction. So here what we can assume here, if product is more stable, more rate of reaction. If reactant is more stable, less rate of reaction. Okay, so this is about the physical states of reactants. Okay, and next when you come to the chemical nature, chemical nature chemical nature of reactants, chemical nature of reactants. Okay, so in case of chemical nature, we are going to discuss ionic reactions and covalent reactions, ionic and covalent reactions, covalent. Okay, so here ionic reactions are very fast when compared to the covalent reactions. Why ionic reactions are very fast when compared to the covalent reactions, means children? So in case of ionic reactions, there is no need of breaking and making of a bond. Simply what they will do, they exchange their radicals. See, for example, you take barium chloride BaCl2 plus sodium sulfate Na2SO4. Okay, so barium chloride aqueous solution, sodium sulfate, it is also aqueous solution. In aqueous solution, barium chloride exists as Ba plus 2 and Cl minus 2Cl minus, and sodium sulfate exists as 2Na plus and SO4 minus 2. Okay, so this is present in one container, and this is we are going to take in one container. So consider it is the BaCl2, barium chloride aqueous solution. So here how the barium chloride exists as, children? Ba plus 2 and Cl minus, separately it exists as ions. And when come to sodium sulfate also, in aqueous state, how it exists? Na plus and SO4 minus 2, means already they are separated into ions. So when you mix these two solutions, what will happen? Simply barium is going to be combined with the sulfate ion, barium is going to combine with the sulfate ion. This is the sodium sulfate. So when you mix them, barium is combined with the sulfate ion and form as barium sulfate. Barium sulfate as the precipitate. Precipitate, what is the meaning of a precipitate here? Precipitate means insoluble solid in a liquid, that is called what? Precipitate. And sodium chloride 2NaCl. Okay, so this is a very fast reaction. It is why it is very fast reaction, because here there is no need of any bond making and bond breaking. Simply what they will do, they exchange their radicals. Okay, so when they exchange their radicals, means they exchange their ions. See, for example, initially barium with present with the chlorine, and after barium is present with the sulfate ion. Okay, so simply what they have done, they exchanged their radicals and there is no need of breaking and making of any bond. But when you come to the covalent reactions, okay, in case of covalent reactions, we need to break the old bonds and then after we need to form the new bonds. For example, you consider 2NO plus O2. 2NO plus O2 is gives rise to 2NO2. Okay, 2NO plus O2 is gives rise to 2NO2. So in case of NO, N double bond O is present. So two molecules we are going to take, and in case of O2, here double bond is present. Okay, so here what we need to do, initially we need to break these old bonds. So totally here how many bonds we are going to break? So here 1 mole NO contain 2 bonds, 2 mole NO contain 4 bonds. Here 4 bonds we need to break, and here 2 bonds we need to break, means totally 6 bonds we need to break here. Okay, so So after breaking the 6 bonds, again it is going to be form how many bonds? N double bond O and O, this is single bond O. Okay, so here 3 bonds are forming. Here total 2 moles of NO2 is forming. Total 6 bonds need to be formed. Means here in case of covalent reactions, okay, time is more. Why? Because here bond breaking is also is there and bond making also is there. For this process, some time it is going to be takes place. That's why covalent reactions are slow reactions, and whereas ionic reactions are very fast reactions. Okay, so here what we can write, ionic reactions. Ionic reactions are fast. Ionic reactions are fast when compared to the covalent reactions. Okay, what is the simple reason here we need to give, children? In case of ionic reactions, there is no need of breaking and making of bonds. Okay, but in case of covalent reactions, here we need to break the bonds. Old bonds we need to break and they should form the new bonds. Okay, that is the reason. That's why ionic reactions are fast when compared to the covalent reactions. Okay, next let us see the effect of concentration of reactants. Okay, so here rate is directly proportional to concentration of reactants. Okay, so if concentration of reactants increases, rate of reaction is also increases. Okay, concentration of reactants increases, rate of reaction is also increases. So how we can prove that concentration is directly proportional to rate of reaction? For example, you take the wood, burning of wood in presence of oxygen, only oxygen, burning of wood, you take burning of wood. Okay, burning of wood, burning of wood, burning of wood in presence of oxygen, and you take the burning of wood in presence of air. Burning of wood in presence of air. So which is the fast reaction and which is the slow reaction? So here what is the difference between O2 and air? Air is a mixture of gases. Air is what, children? It is a mixture of gases. So it contains how much percentage of oxygen, children? Only 21 percentage of oxygen. Only 21 percentage of oxygen. Here complete O2 means here 100 percentage of oxygen is present. 100 percentage of oxygen is present. Okay. So when you do the same reaction in presence of O2 means 100 percentage of oxygen, and in presence of air, air is nothing but it contains only 21 percentage of oxygen. Okay, this is the fast reaction and this is the slow reaction. Fast reaction and slow reaction. Fast reaction means it occur within the less time when compared to the second one. Okay, so here why it is fast reaction? Because more concentration of oxygen, and here why it is slow reaction? Because less concentration of oxygen. So concentration increases, children, rate of reaction is also increases. Okay, so this is about the effect of concentration. And next, if you see effect of pressure. Okay, so we know already according to ideal gas equation, PV equal to nRT. Okay, therefore P is equal to N by V into RT. So now here RT if you take as constant, pressure is directly proportional to number of moles by volume in liter. Number of moles by volume in liter, that is nothing but concentration. Pressure is directly proportional to what? Concentration, which means rate of reaction is also directly proportional to the pressure. Pressure of reactants increases, rate of reaction is also increases. So rate of reaction is also directly proportional to what, children? Pressure. Okay. Next we are going to see the effect of temperature. how the temperature is going to be effect on the rate of reaction. Okay, so here rate of reaction is directly proportional to temperature, whether it is exothermic reaction or endothermic reaction. No matter, if you increase the temperature, rate of reaction is also increases. Okay, means temperature is directly proportional to rate of reaction. Okay, so now here we are having one term, that is temperature coefficient. Temperature coefficient. Temperature coefficient. So here, what is the temperature coefficient for every 10 degree rise in temperature? For every 10 degree rise in temperature, rate of reaction and rate constant approximately become 2 to 3 times. That is known as what, children? Temperature coefficient. Okay, what is the definition of temperature coefficient? For every 10 degree rise in temperature, for every 10 degree rise in temperature, 10 degree rise in temperature, for every 10 degree rise in temperature, rate of reaction, the rate of reaction and rate constants and rate constant becomes, or rate constant becomes double, becomes twice or thrice. Rate of reaction and rate constant becomes twice or thrice. Twice or thrice. Means it changes to 2 to 3 times. Okay, that is the meaning of the temperature coefficient. So how we can express the mathematically temperature coefficient? KT degree Celsius plus 10 by KT equal to 2 power n. Okay, so now here what is the n value? So here n is equal to T2 minus T1 by 10. This is the n value. Okay, see, for example, consider at 30 degrees Celsius, rate constant is, or rate of reaction is 4, and what is rate of reaction? Rate of reaction at 80 degrees Celsius. Like that they have given question. So now how we are going to solve such type of questions, means children? Simply what we know, so here KT degree Celsius plus 10 by KT equal to 2 power n. First n value you find out. Okay, so what is the n value? N equal to what, children? T2 minus T1 by 10. So what is the T2? 80 minus 30, T1 30, that is by 10, means 50 by 10. 50 by 10 means 5. Means how many? So what is the n value here? 5. Means what is the rate? What is the rate at 80 degrees Celsius? 80 degrees Celsius, that is 2 power 5 times. Okay, 2 power 5 times. Sorry, not 2 power 5 times. 2 power 5 times into original rate. What is the original rate? That is 4. 2 power 5 times into original rate. Okay, so this is about the rate of reaction at the 80 degrees Celsius. Okay, in this way we are going to be calculated. So here what you need to remember, children, rate of reaction is directly proportional to temperature. And what is the temperature coefficient? What is the temperature coefficient? For every 10 degree rise in temperature, For every 10 degree rise in temperature, rate of reaction and rate constant approximately will become 2 to 3 times, twice or thrice. That is the temperature coefficient and temperature coefficient formula, and what is the N formula here, and one model problem to find out the rate of reaction at different temperatures. Okay. Next, let us see the Arrhenius equation at different temperatures. Okay, what we need to discuss? Arrhenius equation at different temperatures. Okay, so what is Arrhenius equation? We know that is ln k equal to ln A minus EA by RT. So this is the Arrhenius equation. Okay, at temperature T1, at temperature T1, K is equal to K1, K equal to K1. So now what is the Arrhenius equation? We can write ln K1 equal to ln A minus EA by RT1. Consider it as the equation number 1. Okay, at temperature T2, at temperature T2, K equal to K2, and what is the Arrhenius equation? We can write ln K2 equal to ln A minus EA by RT2, EA by RT2. Okay, consider it as the equation number 2. Okay, so now let us do the 2 minus 1. Okay, 2 minus 1. So subtract the first equation from the second equation. Okay, so now if you do so, what will get, children? ln k2 minus ln k1 means LHS we need to subtract. Okay, LHS we need to subtract. That equal to RHS minus RHS. Okay, that is ln A minus EA by RT2 minus ln A minus EA by RT1. Okay, so now here ln K2 minus ln K1 formula will become what, children? ln K2 by K1, ln K2 by K1, that equal to ln A minus EA by RT2. So minus into plus minus ln A, minus into minus plus EA by RT1. Okay, so now here plus ln A minus ln A will get cancelled out. Okay, so now what we can write this equation as, children? ln K2 by K1, ln K2 by K1 equal to, okay, first you write the plus term, then after you write the minus term. Okay, or else minus EA by RT2 plus EA by RT1 plus EA by RT1. Okay, so here EA by R you take common, or else rearrange that equation. ln K2 by K1 equal to EA by RT1 minus EA by RT2. Okay, so now EA by R you take common now. So ln K2 by K1 equal to EA by R, if you take common, what will get here? 1 by T1 minus 1 by T2. Okay, so or else you can take this equation as ln K2 by K1, ln K2 by K1 equal to EA by R. Okay, so take LCM here, T2 minus T1 by T1 T2, T1 T2, and this equation we can write it as ln K2 by K1 equal to EA by R. T2 minus T1 we can write as the delta T by T1 T2. T1 T2 like that we are going to be write here. Okay, and in place of ln, if you want to write the log, what you need to do, you need to multiply to the 2.303. If you send the 2.303, it will become as log k2 by k1 equal to EA by 2.303 or delta T by T1 T2. Okay, this is the Arrhenius equation which is used to calculate the rate constants at different temperatures. Okay, it is used to calculate what children, rate constants at different temperatures. When you know activation energy and temperature 1 and temperature 2, and out of K1 and K2, if you know K1 you can calculate the K2, if you know K2 you can calculate the K1, or else you know K1 and K2, T1 and T2, you can calculate what, activation energy. Okay, this is the formula find for the ratio of rate constants at different temperatures. Okay, so this is about what children, Arrhenius equation, and Arrhenius equation at different temperatures. Okay, so simply what is there, ln k equal to ln A minus EA by RT. So condition 1, temperature 1, that is equal to k equal to k1, we written Arrhenius equation, and temperature 2, k equal to k2, we written Arrhenius equation, we subtracted. So when you solve mathematically, you will get the final equation on this. Okay, next we'll see effect of catalyst. Okay, first we need to see what is the meaning of catalyst. Okay, what is the catalyst? Okay, so catalyst is a chemical substance which can alter the rate of reaction without undergoing any change. That is known as what children, catalyst. Okay, how we can define a catalyst? Okay, so it is a chemical substance. It is a chemical substance. Is a chemical substance. Is a chemical substance. Is a chemical substance which can alter the rate of reaction. Which can alter the rate of reaction. Alter the rate of reaction. Rate of reaction without undergoing a change. Without undergoing a change. Okay, that is known as what children, catalyst. Okay, alter means what children, it can increase the rate of reaction or it can decrease the rate of reaction. So based on that we can say, for example catalyst. Okay, catalyst can be classified into two types, that is positive catalyst, positive catalyst, and negative catalyst, negative, positive and negative catalyst. Okay, positive catalyst and negative catalyst. Okay, so what is a positive catalyst? Positive catalyst increases the rate of reaction. Okay, it increases the rate of reaction. It increases the rate of reaction. Okay, so the catalyst which increases the rate of reaction, that is called what children, positive catalyst. And negative catalyst, what is a negative catalyst? The catalyst which decreases the rate of reaction. Okay, so negative catalyst decreases the rate of reaction, rate of reaction. Okay, so now how a positive catalyst increases the rate of reaction? By decreasing the activation energy. Okay, so what the positive catalyst can do children, it decreases the activation energy. It decreases the activation energy. activation energy. Okay, so positive catalyst, what it will do, it decreases the activation energy, and negative catalyst, how it decreases the rate of reaction, by increasing the activation energy. Okay, so here what it will do, it increases the, it increases the activation energy, activation energy, increases the activation energy, activation energy. Okay, so now let us take the energy profile diagram to understand the what is the catalyst, how it going to be effect on the rate of reaction. Okay, so now consider here, okay, okay, right. Now consider the reaction. Okay, so it is the reactant, R is the reactant. Okay, so that R, the reactant, is converting into a product P. So this is the R and this is the P, product P. Okay, so now consider a reaction is occurring, it is without catalyst. Okay, this is occurring without catalyst. Now what about this? This is the threshold energy in without catalyst, and this is the activation energy in without catalyst. Okay, this is the activation energy, activation. Okay, without catalyst. Now let us consider one more. So we are going to take a positive catalyst. Okay, so this is the positive catalyst. Okay, and in presence of the positive catalyst, this is what children, activate threshold energy. And what about this? This is the activation energy. Okay, so consider it is what children, without catalyst. The red one we are going to consider is the without catalyst, without catalyst, without catalyst, and this L1 what we are going to consider with positive catalyst, with positive catalyst, with positive catalyst. Okay, so in case of positive catalyst, what is happened here children, the activation energy is decreased. Okay, consider here, this one you consider it as the EA, one you consider this is the EA. So now here activation energy 1 is less than activation energy. Okay, now activation energy 1 is less than activation energy 2. Consider it as the activation energy 2. Okay, so this is with the positive catalyst, and it is without catalyst. Okay, in case of positive catalyst, what is happened here? What is happened? Threshold energy is decreased. Okay, in with the positive catalyst. So here positive catalyst, positive catalyst, what it has done children, it decreased the threshold energy. Okay, threshold energy, threshold energy decreases, threshold, threshold energy, threshold energy decreased, decreased, activation energy is also decreased, activation, activation energy, activation energy is also decreased, activation energy is also decreased. Okay, right, and when you see the, when compared to the without catalyst, without catalyst we can find out more threshold energy and more activation energy, more threshold energy and more activation energy. And next, if you take negative catalyst, okay, so what the negative catalyst will do, okay. So now consider this is the same reaction but with negative catalyst. Negative catalyst we are going to take. So in presence of negative catalyst, what is the activation energy? This is the activation energy. So more activation energy, you consider it as the EA3. EA3, okay. So now here EA1 is less than EA2 when you compare to the EA3. So this is the activation energies, okay. And this is the up to this here, this is the threshold energy. So consider this as the threshold energy 1 ET1, and this is the ET2, and this is the ET3, threshold energy 3. So here also ET1 is less than when compared to the ET2, threshold energy 2, and ET3, okay. So here if you observe very carefully, in presence of negative catalyst, in presence of negative catalyst, what is happening, children? So activation energy increases and also threshold energy is also increases, okay. So that's why rate of reaction decreases. We know if any reactant molecule want to be converted into product, it must cross the energy barrier, okay. So in case of positive catalyst, there is a less activation energy and less energy barrier. In case of positive catalyst, less activation energy, so that more number of molecules can cross the energy barrier easily within the less time. And whereas in case of negative catalyst, we are having more activation energy, so that very less number of molecules crosses the energy barrier. So to convert the reactant into product completely, it will take more time. That's why in case of negative catalyst, what is happening? The rate of reaction decreases. Why the rate of reaction decreases? Because the more activation, due to more activation energy, less number of molecules are going to cross the energy barrier. In case of positive catalyst, there is a less amount of activation energy, more number of molecules, so immediately they cross the energy barrier and they will give the product. Therefore rate of reaction is more, okay. So this is about the catalyst. And when you summarize about the catalyst, what a catalyst can do and what a catalyst cannot do, okay. So now when you observe the in presence of catalyst and in presence of positive catalyst, in presence of negative catalyst, even without catalyst also, there is no change in energy of reactant and there is no change in the energy of product. Means here there is no change in the delta H. There is no change in the delta H. Okay. So enthalpy of reaction not changes. Okay. What it not changes, children? Enthalpy of reaction not changes. Okay. Catalyst can not change, cannot change. What the catalyst cannot change, children? So enthalpy of reaction delta H, enthalpy of reaction cannot changes. And delta G is the free energy also it cannot change. And delta S, entropy also it cannot change. And Kc, equilibrium constant, Kc also it cannot change, okay. So catalyst cannot change all these things, delta H, delta G, delta S and Kc. And energy of reactants, energy of reactant and product, energy of reactant and product, it cannot change the energy of reactant and product. And what catalyst can change? Catalyst can change what catalyst can change? Catalyst can change the rate of reaction, ROR it can change, and also rate constant also it can change, activation energy also it can change, threshold energy also it can change. Okay, it can change rate of reaction, rate constant, activation energy and threshold energy and path of reaction, path of reaction. Okay, path of reaction and duration of reaction, duration of reaction also it change. Okay, time duration of reaction, time duration, time duration of reaction also it can change. Okay, so this is about the what a catalyst can do, what a catalyst cannot do. Okay, so this is about what children effect of catalyst. Okay, next we will see rate constant in presence of catalyst and in present without catalyst. Okay, rate of or rate constant, rate constant, rate constant in presence of catalyst. Okay, catalyst, when they say simply in presence of catalyst, you can just consider it is a positive catalyst until unless they will give the negative catalyst. In presence of catalyst and in absence of catalyst and in absence 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 of catalyst, in absence of catalyst, in absence of catalyst. Okay, so now let us see, let us take the graph. So consider here, this is the energy profile diagram and this is the energy of reactant and this is giving us product P. Okay, so now it is without catalyst and with catalyst. Okay, this is the with catalyst now. Okay, so this is with catalyst. Okay, consider this is the activation energy 1 and this is the activation energy. Okay, activation energy 1 and activation energy. Okay, so it is what children, this is without catalyst, without catalyst at same temperature, at same temperature, at same temperature. Okay, these are the conditions we are going to be consider and here we are going to write the Arrhenius equation in presence of catalyst and in absence of catalyst. Okay, first condition you take, in absence of catalyst, in absence of catalyst, in absence of what, catalyst, in absence of catalyst. Okay, in absence of catalyst, rate constant, rate constant you consider it as the K1 and activation energy, okay, you consider it as the EA1 and you consider it as the EA2 and activation energy, what is activation energy, you consider it as the EA2, sorry EA1. Okay, and what is the Arrhenius equation, you can write here children, ln K1 equal to ln A. Okay, so how we can write the Arrhenius equation here? Okay, ln K1 equal to ln A minus EA1 by RT, EA1 by RT, consider it as the equation number 1. Okay, in presence of catalyst. Okay, next we are going to consider in presence of catalyst, in presence of what, catalyst, in presence of catalyst. Okay, in presence of catalyst we consider rate constant. Okay, so rate constant, what is the rate constant children? Consider rate constant is equal to K2 you consider and activation energy, activation energy you consider it as the EA2. activation energy consider it as the EA2. Okay. So now what is the Arrhenius equation? You can write ln K2 equal to ln A minus EA2 by RT. Consider it as the equation number 2. Okay. So now what you do, you subtract the equation number 1 from the equation number 2, or else you subtract the equation number 2 from the equation number 1. Okay. So however you can do. So therefore here if you do 2 minus 1, 2 minus 1, if you do the 2 minus 1 or 1 minus 2, however if you want you can do 1 minus 2, you do 1 minus 2 also you do, no problem. Okay. So why? Because here activation energy 1 is greater than activation energy 2. Why we are going to take like this? Here activation energy 1 is greater than activation energy 2. That's why we are going to consider this. So therefore ln K1 minus ln K2 equal to ln A minus EA1 by RT minus, okay, or else you just consider it is in the next page. Next page we will take this one. Okay. The next page you consider. So what you will get here, children? ln K1 minus ln K2, that equal to ln A minus EA1 by RT minus ln A minus EA2 by RT, EA2 by RT. Okay. Therefore here ln K2 minus ln K1 minus ln K2 will become ln K1 by K2, ln K1 by K2, that equal to what you can write here, ln A minus EA1 by RT. Okay. EA1 by RT, EA1 by RT minus plus into plus minus ln A minus into minus plus EA2 by RT. Okay. So now here ln A will get cancelled out. Okay. Right. No problem. Okay. So ln K1 by K2, ln K1 by K2, ln K1 by K2 equal to minus EA1 by RT plus EA2 by RT. Okay. So right, minus EA1 by RT plus EA2 by RT. Okay. Now RT would make common here, ln K1 by K2 equal to or else you write like this, EA2 by RT minus EA1 by RT. Okay. So if you do so, what you will get here, ln K1 by K2 equal to, okay, so 1 by RT or 1 by RT or simply EA2 minus EA1 you will get, or else the same equation only if you write likewise. If you write likewise, that is ln K2 by K1. Here we have inverted, means this equation also is going to be changed as EA1 minus EA2 by RT, EA1 by EA2 by RT. Okay. So now here instead of ln you just write the log. Instead of ln what you do, write the log. So log K2 by K1 equal to EA1 minus EA2 by 2.303 RT. Okay. So here instead of ln what you will write, 2.303 into log K2 by K1 will write. So that 2.303 we are sending that side. Okay, that's why here we are going to get this equation. Final equation it is, that is ln log K2 by K1 is equal to EA1 minus EA2 by 2.303 RT. Okay, this is the Arrhenius equation with catalyst without catalyst. Okay, next we will see the topic surface area. Okay, generally here rate of reaction is directly proportional to surface area. Okay, means the surface area increases, rate of reaction is also increases. So here what is the meaning of surface area? So for example, on this marker what are the places we are going to see, that all things are known as what? Surface area. So if I make it into pieces, we can see the more number of places, means more surface area. Surface area increases, rate of reaction is also increases. Okay, so now here for example wooden log. Okay, wooden log we are going to take, or wooden chips. Wooden chips. Okay, chips means a small pieces of wood, they are known as wooden chips. So which will burn easily? So wooden chips burn easily, but they will not burn very easily and they will not catch fire easily. So not burn, or not burn easily. Okay, burn easily means catches fire very easily. Catches fire easily. So it not catches fire easily. Not catches fire easily. Okay, so this is about what, children? Factors which affect on the rate of reaction. Okay, so what are the factors we have discussed so far? Okay, so we discussed about, okay, we discussed about the nature of reactants and products, surface area, okay, and concentration of reactants, catalyst, temperature, pressure. Okay, so now if you observe, so in case of nature of reactants and products, so nature of reactants and products, first physical nature we are going to take, in that gas is greater than liquid, liquid is greater than solid, and homogeneous reactions are greater than heterogeneous reactions. And stability of reactant inversely proportional to rate of reaction, and stability of product is directly proportional to rate of reaction. Okay, next we discussed about the chemical nature. Ionic reactions are fast when compared to the covalent reactions. And next, concentration of reactants. Concentration is directly proportional to the rate of reaction. Rate is directly proportional to pressure of the gas. Okay, next, or pressure of reactant. Effect of temperature. So temperature is directly proportional to rate of reaction, whether it is exothermic reaction or endothermic reaction, no matter. If you increase the temperature, rate of reaction is also increases. And temperature coefficient, for every 10-degree rise in temperature, the rate of reaction will become 2 to 3 times approximately. Okay, so and based on the temperature coefficient formula and one problem. Okay, next, okay, what is the Arrhenius equation at different temperatures, and what are the rate constants at different temperatures? Next, catalyst. What is a catalyst, and type of catalyst, how a positive catalyst and how a negative catalyst can affect the rate of reaction, and what the catalyst can do, what catalyst cannot do. Next, okay, so rate constant in presence of catalyst and in absence of catalyst. Okay, so these are the equations. So this is the Arrhenius equation in presence of catalyst and in absence of catalyst, and surface area. Okay, so with this I am going to end this topic, and finally I would like to say thank you for listening, and if you like our efforts, please subscribe our channel MK Academic Solutions. Okay, thank you very much.